Hello everybody, today I'm going to be solving problem 1 of Project Euler, which is called multiples of 3 or 5. This problem says that if we list all the natural numbers below 10 that are multiples of 3 or 5, we get 3, 5, 6 and 9. The sum of those is 23. And effectively we want to find the sum of all of these multiples of 3 or 5 below 1000, right? So a slow way of doing this would be looping through every number from 1 to 999 and checking if it's a multiple of 3 or 5, then adding it. But that's really slow. So we're just going to compute the sum instead, directly, with a really cool mathematical trick. So first I'm going to define the function. I'm going to call it sum of 3 and 5s. And we're going to call the parameter UL, upper limit. We only care about the numbers below the upper limit, so I'm going to use UL minus 1 when I'm figuring out how many terms are in each sequence. So we're going to find out how many multiples of 3 there are by this. This works because integer division, which is this here, just gets rid of the ugly decimal portion that we don't need. It tells me how many times 3 fits into 999. And we're going to do the exact same thing for the 5s. And we're going to do the exact same thing for the 15s. This one is especially important because say if I take a random number, 20, and I add the multiples of 3 or 5 below this, as you can see, when I type it all out, this is the sum of the 3s, and this is the sum of the 5s. You'll notice that we're adding 15 twice. This is called double counting, and if we let this happen, it will just make whatever sum we get completely invalid, because we only want to add each multiple once, right? So that's why that's there. And now, we're going to initialize the total. And instead of adding all of these manually with a 4i in range or something like that, we're just going to use a formula, which is that the sum of the natural numbers from 1 to n is equal to n lots of n plus 1 divided by 2. This formula works because if we draw an imaginary line of symmetry down the middle of this, and we add the first and the last term, we'll get n plus 1. If we add the second and the second to last term, we get n plus 1. And if we add the third and the third to last term, we get n plus 1, and we get n plus 1, and we get n plus 1, and so on. And we get this a half n times because there's n terms in this sequence, and we're adding them in pairs, so we divide by 2. So let's do this for the 3s. Total plus equals 3 times the number of 3s times the number of 3s plus 1, integer division 2. And this part is the formula that I just showed you, and then we're just multiplying it by 3 because, well, say if you're doing 1 plus 2 plus 3 and you multiply it by 3, that will just give you 3 plus 6 plus 9, which is what we want. Right, so we'll do that for the 3s, we'll do that for the 5s, and we'll do it for the 15s. However, we're going to subtract this one, just to make sure that the multiples of 15 are singly counted and not double counted. Like I said before, if we were doing the sum of the 3s and the 5s below 20, let me just type this out really quick. Then by doing this, we're effectively just cancelling out one of these 15s, which this sum is actually what we want, which is fantastic. And that is literally the problem solved. If we have a look, we should get, I think it's 233178 or 233168, I think. Yeah, there we go. That's the problem solved. Thank you for watching. See you in the next one. Bye bye.